So we'll make a start. Okay. So today I'm going to be talking about theory and practice of native mass spec. We're going to cover why do you need to do native mass spectrometry? What do we mean when we talk about native? We'll cover the instrumentation, we'll cover sample preparation, sample acquisition, how we do mass analysis, multi-assignment. I'm going to spend quite a lot of time on this because I believe this is fundamentally important, and finally how we do charge state distribution analysis. Okay, so there are essentially three experimental approaches to protein mass spectrometry. The first one you're probably familiar with. This is a bottom-up approach, a MSOS approach. In this approach, we generate partial sequence data. We generate homology. We're able to identify proteins by homology, and we can identify known post-translation modifications. And the analysis the analogy I would give is that we identify by homology. We know this is egg because it is like egg. Top down, we spoke about this in the fourth session. Top down, proteins remain intact under denaturing conditions. We use accurate mass measurement to determine structure, identity of the protein, and known post-translation modifications. The analogy here is we can have some idea of what type of egg it is because we're retaining structural information. And finally, native mass spectrometry. Again, proteins remain intact, but they do so under native conditions. We are able to make accurate mass measurement. We can determine molecular interactions in addition to the information we already get from here. So we get all of this information, plus molecular interactions, plus we get from the charge state distribution, we can determine the size, stability, and conformational folding. So my analogy here is you are now able to look at the protein's function as well as its structure. And native mass spec is the most powerful benchtop analytical technique available to you. Just say something about quality control. A lot of people are working on recombinant proteins. They're used for a variety of purposes. Whatever the purpose you're going to use your protein for, quality control is absolutely essential. You want to know that your protein is going to be the same from one batch to another. So you need identity, post-translation modifications. You want to know if there's any degradation happened, mutations. You need to know the purity. These last two things, you need to know the specific activity of your protein. You need to know the monodispersity of your protein. Conventional denaturing mass spec does not yield any information on this. So it's very, very important to have this data, and native mass spec is one of the best ways of getting it. So what does native mean? I'm going to paraphrase Theresa May. Native means exactly that, native. What do I mean? I mean it must retain all the characteristics of the native state. This is how it's defined. These are activity, structure, conformational stability, the ability to specifically bind ligands, protein-protein interactions, must retain the same complex stoichiometry, and the protein is either in its correct folded conformation or it isn't. There's no halfway house. You either have live protein or not. If a protein is non-native, it's either partially unfolded or it's completely unfolded. And obviously for most proteins, although not all, for most proteins, denaturation is irreversible. And I can illustrate that by native mass spec. So this is a conventional spectrum, conventional denaturing mass spectrum from BSA. You don't normally see this because the software will deconvolute the spectrum for you. But when you do that deconvolution, you are losing all of the structural data. You just get the mass. In a native mass spec experiment, the mass is actually usually not particularly of interest. What is of interest is the structure, and the structural information is in the charge envelope. Now what you typically get in a native experiment is you will get 3 charge envelopes. This one is the denaturing charge envelope. This one here, you may or may not get this, but this is, in this case, this is partially unfolded structure, and this is the native structure. Okay? If I denature this protein, this will disappear. And these 3 charge distributions can only be explained by this being a native structure. To my knowledge, nobody has ever put forward an alternative explanation for these 3 ion distributions. So, what does native mean? Well, we have the duck test. The duck test says if it looks like a duck, and it walks like a duck, and it quacks like a duck, it's got to be a duck. People talk about near native, or people will talk about native in inverted commas. This is completely meaningless. You'll hear people talking about using supercharging reagents. Do not use these, they are denaturants. People use ion mobility. Ion mobility, it describes the behavior of gas phase ions. They may or may not reflect conditions in solution. You simply do not know. However, native mass spec, it describes and quantifies the protonation state. In other words, the charge assignment on your ion, and ionization cannot occur in the gas phase. There's a thought experiment you can do. If you imagine you can measure the droplet volume, as you have electrospray droplet and desolvation occurs, that volume is going to decrease until you reach this point. At that point, once the volume of the droplet is the same as the volume of the protein, by definition, all of your solvent is gone. By definition, you are no longer in the liquid phase, you are in the gas phase. But ionization cannot happen in the gas phase. It's already happened. So basically, your ionization, your assignment of charge, either has to happen at this desolvation point or before, but it cannot happen afterwards. And that's important because basically what it means is when you are measuring the mass to charge is determined by the protein condition immediately preceding this ionization point. In other words, the liquid phase. And just to illustrate that, this is an ion mobility QTOF. Here's your ion mobility cell, and the drift time, this is determined and it's also measured in the gas phase. Your MZ measurement happens also in the gas phase, either in the quadrupole or here in the top tube, but your assignment of charge happens here during the ionization process in the liquid phase. A lot of people tell you need special instrumentation for native mass spec. You don't. Any electrospray instrument can be used for native mass spec. You cannot use MALDI. The critical thing is this MZ. How far up the MZ range can you go? Older instruments will have a mass limit of 3,500 typically, and that will enable you to measure to do native spectra up to 445 kilodaltons. You can use static nanospray, but it's not essential. Collisional cooling is beneficial. I'll show you some data here, but it's not essential. Ion mobility is certainly not essential, and use of an Orbitrap. In theory, this will give you higher resolution. However, that resolution is compromised at high MZ, and QTOF is actually better. Just to show you, this is an example of a just did this just to prove a point. This is a native spectrum of BSA. This is acquired on our oldest ion trap system upstairs. This has an MZ limit of 6,000, so you can measure complexes up to about 90 kilodaltons. So sample preparation for native mass spec is extremely important, probably the most important thing. Your proteins have to be desalted. That's essential for mass spec, and you have to do this into a mass spec compatible buffer. That means that the salt has to be volatile. So they're typically ammonium salts. For membrane proteins, your buffer has to include a detergent. This is normally at either 1.5 or 2 times the CMC. Obviously, native conditions have to be maintained. If you fail to maintain native conditions, you're not going to get a native spectrum. For this reason, your protein should be freshly prepared and held on ice prior to analysis. I don't see any point in doing native mass spec on a sample that's been cold, been in the fridge, or it's been through several freeze-thaw cycles. So avoid freeze-thaw. As I mentioned, we can't use reverse phase chromatography. We can't use organic solvents, they're denaturants. We can't use ion pairing reagents, they're also denaturants. However, most proteins will tolerate around about plus or minus 1 pH unit around their pH optimum without actually denaturing. And you can see this in the native spectrum. Also, do not use DMSO. So here's an example of some buffers that you can use: ammonium acetate, ammonium formate, ammonium bicarbonate, slightly higher pH, which is useful. This is a native buffer. These two enzymes, the pepsin is active in hydrochloric acid, pH 2. So you can spray it in this buffer and it will maintain its native conformation. Various buffer exchange methods are available. The most popular one is this, use of gel filtration spin columns. These are the columns we use, these microbiospin columns. You pass your sample through the column 3 times. There's quite a lot of wastage when you do that, so you need quite a lot of protein. You need about 50 micrograms of protein to do it. The smallest of these will allow you to work with a volume of 75 microliters. A gentler method is dialysis. Sometimes your complex can fall apart if you desalt it too quickly. Sometimes beneficial to do it more slowly. Same buffer, but by overnight dialysis. Another way you can do this is you can use size exclusion MS. Okay, so this is inline automated desalting by size exclusion chromatography. It's an inline method, so you can automate it and it goes straight into the mass spec. In terms of acquisition, you can use direct infusion. So remember, you're bypassing the HPLC system here. We use a syringe pump. You can also use this by a static needle. Low flow rate is absolutely essential. Upstairs we would typically use 6 microliters a minute, and we can do this using a standard 30 gauge stainless steel nebulizer. You must optimize desalvation conditions. So we would use dry gas flow of 5 liters a minute, nebulizer pressure of 17 psi, and drying gas temperature of 325 degrees. That comes as a surprise to a lot of people. How come you can do this? Okay, well, you can. And the reason you can is because you have this phenomenon of the latent heat of evaporation. So as your electrospray droplet is cooling, so as it's in this hot gas stream, the latent heat of evaporation has got to come from somewhere. It's in a vacuum. So that energy has to come from the droplet itself. So the droplet is cooled as desalvation happens. And the analogy I would make here is in the sauna. If you're sitting in the sauna, the temperature can be 90 degrees Celsius. You don't die. The reason you don't die is because of latent heat in evaporation. Here's an example of automated inline size exclusion mass spec. So this works from this can work from 96-well microtighter plate. The desalting is in line by size exclusion chromatography. Runtime is 6 minutes per sample. It's automated. Big advantage of, well, multiple advantages. One is that you can automate it. Another advantage is you can get away with loading a lot less protein. So 1 microgram of protein, that's similar amount that we would use for a denaturing acquisition. We can automate the deconvolution. We can therefore do very rapid data analysis, and this is ideal for compound screening. And here's an example. This is a mock screen, and we've used 2 micrograms of BSA in the 96-well plate. And here I'm showing the reproducibility of the peak intensity, and here's this reproducibility of the mass accuracy. And these are the typical spectra that we get. Okay, so obviously the instrument has to be tuned to high mass to charge. We do that by, usually we have this as high as we can make it, this fragmentation voltage, or in other instances, Coulomb voltage. On our instruments, we can change detector mode. If we go to 1 gigahertz mode, this allows us to measure the mass to charge from MZ 500 up to MZ 20,000. In our normal 2 gigahertz mode, we would only go up to 3,500. But this is not particularly high. Other instruments, more modern instruments, can go up to 40,000 MZ. We use collision gas, 40 pounds per square inch, and we can do something interesting with the detector. We want our best chance of detecting these high mass ions in a spectrum, in a mass spectrum above MZ 2000. Effectively, there is no noise. So you can take advantage of that by turning the detector gain up to maximum, because there's no noise to amplify, just the signal. Membrane proteins. So membrane proteins is a slightly different technique. We have to lower the fragmentation voltage so we can apply collision energy, and we have to optimize that. Collisional cooling, it was discovered quite a long time ago. Collisional cooling is important for a native mass spec. The reason is your high MZ ions are difficult to transmit through the ion optics, and collisional cooling is found to be beneficial. So your ions have less energy. On QTOF instruments, this is done here at the Q0 quadrupole. So we can't do this on our instrument. We don't have the option we don't have Q1. We don't have the option of introducing a cooling gas there. However, quite surprisingly, if you add cooling gas and the collision cell, this will increase the ion transmission by about threefold. So it has a similar effect. So let's have a look at how we do the mass analysis. Okay. Native mass spec is informative, but it's much more informative when you can compare spectra with each other. And one of the comparisons that we always do is we compare denaturing spectrum with a native spectrum. Okay. So you acquire denaturing mass spec in the normal way. You acquire your native mass spec by direct infusion. We generate the MZ spectra, deconvolute, and then compare the neutral spectra. And this is typically what you may find. Now, you don't always see this, but if you do see it, so this is your spectrum, your denatured spectrum. That's your expected unmodified mass. These are sodium adducts. In your native spectrum, most of the sodium adducts have gone, but we now have this second peak. And this, as you can see, this is plus 64. This corresponds to either addition of zinc or copper. It's far more likely to be zinc. So this comparison here tells you that this must be a non-covalent interaction. And it's very common to see this in a native experiment. So native spectra, they will often have a lower resolution and lower mass accuracy than a denatured spectrum, especially above 100 kilodaltons. Vendor deconvolution software is not really designed for native mass spec, so it has difficulty distinguishing between multimers, because the singly charged monomer has the same mass to charge as the doubly charged dimer. It has the same mass to charge as the triply charged trimer. And for some reason, vendor software does not deconvolute above 750,000. In most cases, the mass is already known. You've already measured the mass by denaturing mass spec. but you need this for the charge calculation. However, nearly all information content in the native spectrum doesn't come from the deconvoluted spectrum, it comes from the charge state distribution. So one piece of information you can get from the charge state distribution is stoichiometry. This is a spectrum for beta-galactosidase. It's a tetramer. The mass of the tetramer is just under 450,000. And so you can see there are three distinct charge distributions here. 1, 2, 3. We can use the mass, the measured deconvoluted mass, to input into this. This is the charge table. And what you have on the charge table is for every multimeric state and every charge state, you calculate the mass of the charge. And when you do this, you discover that this distribution will only match here in the monomer part of the charge table. This distribution will only match here as a dimer, and this distribution will only match for the tetramer. There is no trimer. And that's exactly what we would expect, because this is the crystal structure for beta-galactosidase, and it is predominantly a tetramer. Here's another example where we determined stoichiometry for a membrane protein, and it turns out this membrane protein is a trimer. These structures here that I've labelled in red, these are an artifact of the collisional activation that you need to do in order to remove the detergent. So protein complexes are important, particularly in native mass spectrometry. Okay, this is an example of a complex that we've measured in the SDC, and this is an iron sulfur cluster, and it has 5 different components with a stoichiometry of 2 to 2 to 2 to 2. I know that because I've measured the mass of the individual components, I've measured the mass of the complex, and the only way you can achieve that mass is by this stoichiometric ratio. And that's the only way you can do it, shy of crystallography. Here's a crystal structure, and you can see that it mirrors this 2 to 2 to 2 to 2 to 2. Okay, I want to talk now about understanding the charging mechanism. Okay, I'm going to make a statement here, and what I'm going to say is that native mass-to-charge spectra, they can only be interpreted correctly if the mechanism determining the charge and the intensity for each ion is understood. Okay? I think that's possibly obvious, but I'm going to have to say that. Okay? And I'm going to take you back to 20th of January 2014. That's an important date for me because that was the day we obtained our very first native spectrum for this complex. So very first native spectrum at the SGC. Before I show you that spectrum, I want to show you what I was expecting to see. Okay? I've read some papers on native mass spec, and I was expecting that the charge state was going to be higher. If you take a similar protein, something of similar size, so this is beta-galactosidase, this is the MZ spectrum for the denatured protein. This complex has a mass of 124,000. Beta-galactosidase is slightly smaller, but you can see it has over 100 observable charge states. What I was expecting is I would get something similar but shifted to higher MZ. This is what I actually saw. And I can say this spectrum taught me something really, really, really important. What it taught me is that I actually understood absolutely nothing about electrospray. Absolutely nothing. I want to show you another spectrum now. This is an earlier spectrum we generated with beta-galactosidase. And you can see we have three distributions like the previous one. This is the monomer, this is the dimer, this is the tetramer. We're able to calculate that from the charge distribution. And we know something about the relationship between these. We know that this is monomeric, this is dimeric, this is tetrameric. So what is the relationship between these multimeric states and the charge state that you actually observe? Well, I did a little back of the envelope calculation, and I simply assumed that beta-galactosidase, as a tetramer, I found its diameter is 12 nanometers. If you just simply work out the surface area for the tetramer, if you imagine that the dimer just has two additional surfaces and the monomer will have another additional surface, and you calculate the surface area, and then you divide that by the average charge state, what you discover is that the charge density is almost exactly the same. So I'm thinking, well, that's extremely interesting. Maybe I've discovered something that wasn't known before. But actually, when you go into the literature, what you discover is this is already known. This has been known for quite some time. And what this paper says is that if you take, there's roughly 20 model proteins here, you take the crystal structure, you determine the solvent accessible surface area for these 20 proteins, and then you plot it against the average charge state, you get, near as damn it, perfect straight line. This isn't chance. You don't get this type of relationship in biology. You get this type of relationship in physics. Everybody knows this. Everybody in the field of native mass spec, they know this. They've all read this paper. But nobody talks about it. Why does nobody talk about this? Because for my money, this is one of the best papers I've ever read. It's one of the most significant pieces of data I have ever seen. People don't talk about it. Why don't they talk about it? Well, the reason is scientists are human beings. Humans, they don't see what's there, they see what they're expecting to see. I just want to illustrate that. This is what's called an Ames run. This is a classic experiment in psychology. Okay? There is no manipulation of the video. This is real. Yeah? It's not what you're expecting to see. But you have to learn, as scientists, you have to learn to see what's actually there in front of you. It's lovely, isn't it? You watch it all day. So there is a scientist working in Italy, Rita Grandori. She basically said, well, if there is a relationship between surface area and charge for a native protein, surely there should be a relationship between surface area and charge for a denatured protein. So she'd done this experiment, and what you can see is, well, yes, there is kind of a relationship, but it's not totally convincing, is it? She had the right idea, just did the wrong experiment. In the SGC, we did the right experiment, right? What Rita did is she measured the average charge state here. What we've done is we measured the maximum charge state. What you will notice if you do any protein mass spec is this value never exceeds 600 Daltons, ever. If you plot this against, what I've done here, I've plotted the maximum charge state against just the residue number for the protein, you can see that almost all of these proteins sit on a beautiful straight line. The R squared value for this is 19.99. However, you can see we do have some outliers. These green ones here, they're all sitting below the line. They all have something in common. What they have in common is they are disulfide bonded. If you reduce those proteins, what you see is they all sit on the line. Here's another experiment that really surprised me when I did it. This is a comparison of two different proteins. So this is myoglobin, and this is lysozyme. This is a normal denaturing spectrum for myoglobin in 50% methanol, pH 2. If you analyse the same protein, this is the native spectrum, because we've got two species here, because we've got the hollow protein and the apo protein. But that's typically how you'd expect the protein to behave. However, when you do this with lysozyme, what you see is the denatured spectrum and the native spectrum are almost exactly the same. Why is that? Well, I used to work on lysozyme. Lysozyme has 4 disulfide bonds, and also it's massively heat stable. You can boil lysozyme, cool it down, and it will still retain its activity. What's happening is, so this charge here, this is not coming from the pH of your buffer. The reason you have this higher charge state is because the protein is unfolding. So the pH influences unfolding, but unfolding is the thing that determines the charge state. Just to illustrate that again, this is BSA. This is a fresh preparation of BSA, and you can see almost all the protein is in its folded conformation. pH 6.5, there's a small amount of unfolded protein here. If you take another preparation of BSA that's extremely old, this has been sitting in the fridge for about 6 years, something like that, and we can still see we've still got the folded structure, but now a considerable portion of the protein is partially unfolded. If we denature it, we can increase the charge state, pushing the charge envelope down to the lower MZ, but BSA has 19 disulfide bonds. You have to break all of those bonds before you can push the charge state down to here. So what's going on here is BSA is becoming linearized. If the disulfide bonds prevent it from linearizing, but if you break those bonds, BSA can now adopt a linear structure, which is here. People will tell you, if they do MSMS of bottom-up mass spec, they will tell you that if your protein has is a basic protein, it will ionize more readily in positive ion mode. I don't know why people say this, because they've not done the experiment. I have done the experiment, okay? This is with tryptic and chymotryptic peptides from BSA. 82 different peptides. If you plot here the number of basic residues against the charge state, what you see is there is no real relationship between them. Pretty much random. However, if you take